Collision detection through a visual fence is crucial for enhancing the safety of collaborative robotic arms. Existing works typically perform detection based on pre-deployed, stationary cameras located outside the robotic arms workspace. However, these stationary cameras limit the mobility of the robotic system and can only provide a restricted detection range. To cope with this issue, we introduce a collision evaluation-based active sense system to facilitate collision detection for collaborative robotic arm considering uncertainty. This system is implemented alongside the robotic arm for real-time tracking of collision risks. Firstly, an active vision mechanism is implemented to fully observe dynamic obstacles within the workspace. Based on the perception information, we design a state confidence envelope to uniformly characterize the state and certainty of both known and potential dynamic obstacles. Subsequently, using observation-based uncertainty evolution, we predict the future states and uncertainty for each confidence envelope. In consideration of collision risk, several vision states are generated, and a Markov decision process is employed to identify the safest observation sequence. Finally, our active vision mechanism adjusts the camera to the previously mentioned sequence for collision detection, allowing the robotic arm to avoid collisions if any are detected. Real-world experiments were conducted to validate the security and reliability of our system. In the first experiment, an operator's hands were positioned at 4 different points to fully demonstrate the high detection range of our active vision mechanism. As shown in the video, our active sensing system effectively detected all obstacles, enabling the robotic arm to successfully avoid them based on the collision detection. The movement of active vision mechanism is shown on the right. In the second experiment, an operator was machining a part within the robotic arm's workspace and engaged in tool transfer with another operator, which blocked the original trajectory of the robotic arm. As demonstrated in Test 2, the CEASE system detected the impact of the operator's machining activity on the robotic arm's operation, prompting the robotic arm to perform its first replanning. Subsequently, when the other operator handed a tool to the first, affecting the avoidance trajectory of the robotic arm, the CEASE system accurately identified the movement of the obstacles. The detection range of the active vision mechanism is showcased on the left. To verify our system's efficiency, we conducted simulation experiments focusing on its tracking capabilities for dynamic obstacles. By comparing the temporal coverage across 3 distinct methods, we established the superior performance of our approach. As illustrated in the subsequent table, our method's average temporal coverage for each body part exceeded that of the fixed camera method by 168% and the TCP observation method by 19.6%. This demonstrates our method's extension of observation, provides a more comprehensive observation of dynamic obstacles over time, enhancing the safety of the robotic arm.